Hey everybody, we're live and in stereo. I've started the recording and I'll just put a smiley face because for now I just want to talk a little with you guys. I hope everybody's taken the recorded lectures. Those who've missed the live classes, I hope they've taken the classes which are available on your portals. I don't know if the portals are issued to you, but if they're not, you can watch the first couple of classes on my YouTube channel by the name Carboxyl by Carboxyl, by on Carboxyl, no. Yeah. Sir, salam alaikum. After class, can I show you something I've been working on, like a website helping people understand finance? That's awesome, Abdulrahman. You're doing a wonderful job for sure, for sure. But probably not after class because after class I'll have to rush back to the office. Maybe on the weekend, huh? So inshallah on the weekend we'll look into that. But please guys, those who are not joining the live classes, because I know it's summers and we have over 70 kids registered, but you if you're still missing the classes because you are partying and you are going around traveling the world, it's a-okay, but do watch the recordings. Don't pile them up for yourself, because at the end, it's a circle of life. It happens every year. Then when near the exam, students start to cry, oh my god sir, I wish I had studied before, da, da, da. So I can't really change this attitude because it's been going on for the past hundreds and hundreds of years. So it's going to go on in this session as well. Students are going to miss out on classes, they're not going to watch the recordings, and they're going to get confused, and then no matter how well you teach, they will slack behind. And that is the reason why not all students get straight A's in AS level, because they just start to slack off. They just take everything for granted. So do have studies as one of your priorities. If not your priority, one of your priorities, right? Okay. Sir, hafta itwar jaldi nahi uta jata. Hamza, watch the recording later on. If you can't join the class on Saturday, Sunday, it's fine. You can watch it. The timing is going to change probably, inshallah, after the next in the next 10 days or so, because I have also a professional career to cater to. So I have some professional commitments, some reservations, due to which I'm not able to take the classes in weekdays. But that'll change, inshallah. Okay, let me give you guys a quick recap. Can I get a Gucci in the chat box? Yes. Can I get a Gucci in the chat box? Yes, Mahad, you can. When will the portal be ready for recordings? यार हो जाएगा, upload हो जाएगा, chill. No, not Prada. Gucci. Yes, thank you very much. Thank you. So we started off with something known as electronic configuration, and this term literally referred to what? It referred to the distribution of electrons in shells. And now in A levels we call those shells principal quantum numbers, principal quantum shells. You can also call them shells. You can also call them energy levels and whatnot, right? And then we figured out that these principal quantum numbers are further divided into something called subshells. What in the hell are subshells? Subshells are also known as sub-levels. And subshells or sub-levels, and the principal quantum number is also known as an electron orbit. So orbit, not orbital, orbit is the word used for this. So subshells are basically, it can either be an orbital or it can be a combination of orbitals. So we realized that not all electrons in the same shell have the same energy level, which Bohr said. Remember, Bohr said that all electrons in the same energy level, aka the same principal quantum number, principal quantum shell, orbit, shells, whatever, they will all have the same energy. But Erwin Schrödinger, he proved Bohr wrong. He said that no, sirree, there are also something known as subshells, and because of these subshells, they're in a particular orbit or in a particular shell or in a particular principal quantum number, principal quantum shell, the electrons are not having the same energy, except for orbit number 1, except for principal quantum number 1, because it only has one subshell, which is the S subshell. So except for principal quantum number 1, you are wrong. Only in principal quantum number 1 are all the 2 electrons in the same energy level, because it's just one subshell, right, which is the S subshell. But other than that, if I talk about principal quantum number 2, you have the S subshell and the P subshell, and you realize that electrons in the P subshells are at a higher energy level then S, and that is why you need to fill out S subshell first. S subshell, or electrons in the S subshell, are at a lower energy level. It's just a recap. We already studied all of that good stuff. Why are they at a lower energy level? Well, we have already studied this. When we start to fill out electrons, we first fill out the 1s subshell, then we move on to the 2s, then we move on to the 2p, 2s2, 2p6, and so on and so forth. Why do we fill the s first? Why do we fill the s subshell before the p subshell? Because we studied that electrons first of all, they occupy the lowest energy levels. So electrons always occupy the lowest energy levels, right? That's called the Aufbau principle. What's the spelling of Aufbau? I've forgotten the spelling. Aufbau. A-U, it's like a German one. A-U-F-B-A-U, I guess. A-U-F-B-E-U. That's called the Aufbau principle. And why does this happen? The why is not in your codes, but I told you guys the reason for that is to minimize the total energy of the atom, the total energy of the atom. That makes the atom more and more stable. So that is the reason why you fill out the s subshell before the p subshell. And we realize that in the subshells, in the p subshell, you actually have orbitals. And how many orbitals do you have in the p subshell? You have 3p orbitals. 3p orbitals. How do I know that I have 3p orbitals? Because an orbital is a region in space where you have the highest probability of finding an electron. Almost 95%, where there's a 95% chance of finding an electron, and an orbital can only occupy a max of 2 electrons, not more than 2. An orbital can only have 2 electrons. Then how can p have 6 electrons? That's the subshell we're talking about. So the p subshell has 6 electrons in total, but a p orbital only has 2 electrons. Remember, orbitals can only have max of 2. Then how is the p subshell having 6 electrons? Because the p subshell actually has 3p orbitals. The only way it can have 6 electrons is if it has 3 orbitals, because each orbital will accommodate 2 electrons. So in the p subshell, you actually have 3p orbitals. So the s subshell is in fact the s orbital, which looks like a sphere right here. The p subshell is a combination of the p orbitals, right? The p subshell has 3p orbitals, so it's a combination of the p orbitals. So you have 3p orbitals: px, py, pz. Px, py is just axes. I'm just naming the axes. You could draw like this the p orbital. You could draw it in the y-axis. You could also draw it in the z-axis. It doesn't really matter. So you have 3 p orbitals, and I've shown you these orbitals in the last couple of classes, right? Now the way we started to fill out the electrons in using our subshell electronic configuration, this is all a recap. How did we fill out electrons using subshell electronic configuration? We said that we always fill out the 1s first, then comes the 2s, then comes the 2p, then comes the 3s, then comes the 3p, then comes the 3d. No sir, before the 3d, remember, always before the 3d you have to fill out the 4s. So remember, 4s is always filled before the 3d. Why? Because 4s is at a lower energy level, and I've explained that in quite a lot of detail in the last classes. But when we write the electronic configuration, Cambridge tends to club the subshells having the same quantum number together. So subshells having the same principal quantum number, Cambridge clubs it. Cambridge says all the 3's should come together. Although we know that if I were to fill this stuff, if this has 2, this has 2, this has 6, this has 2, this has 6, if I were to fill it, I would fill this first and then probably go to the d orbital, right? So always fill out the s before the d. Even if I talk about the 4d, I have to fill out the 5s before it. Why? S before d, always. Why? Because 5s is at a lower energy level than 4d. 4s is at a lower energy energy level than 4d. Yes, and there's one way that teachers help you write the electronic configurations, and that is through a technique. So I've taught you guys a very simple way. It's very logical, it's very conceptual, saying that you have principal quantum number 1, 2, 3, 4. And how do you start to fill it? Well, I first, in the principal quantum number 1, I have one subshell known as the S subshell. So I have to fill out the 1s first. Then in principal quantum number 2, I have two subshells. One is the 2s and the other one is the 2p. So after I fill out 1s, then I have to fill out 2s, then 2p. Then I move on to principal quantum number 3, I fill out the 3s, the 3p, but before I fill out the 3d, I have to fill out the 4s. So fill out the 4s and then I'm gonna fill out the 3d, right? I'll write 3d at the top because it corroborates with this principal quantum number 3, but remember, always fill out the 4s before the 3d. And then after I fill out the 4s, I'm going to fill out the 4p, and then I'm not going to fill out the 4d. Before the 4d, I'm going to fill out the 5s. And in the exam, the examiner will not ask anything above 4s. So he'll only ask till probably here till 4p, not anything above 4p. So this is how you fill it. You fill the 1s, the 2s, the 2p, the 3s, the 3p, and then before the d you fill out 4s, then 3d. But you write it like this. Writing it is something else, filling it is something else. So you fill the 4s first, then the 3d, then the 4p, and then the 4p, and then the 5s, and then the 4d. Right? So that's how you do it. And so scientists, they've made it easy for you. They have come up with tips and tricks. They write something in this order, and then they help you, fill the electrons. They write 1s, then they write 2s, 2p, then 3s, 3p, and 3d, then 4s, 4p, 4d, 4f, and then 5s and whatnot, right? So how do they tell you to fill it? They just make lines. They say first you fill out the 1s, then you fill out the 2s, then you fill out the 2p. You fill it out like this: 1s, then 2s, then 2p comes first, then 3s, and then you fill out the 3p, then the 4s, then the 3d, then the 4p, then the 5s, and then the 4d. That's one way of knowing how to fill the electrons in subshells, right? We're talking about subshells, not about orbitals. We're talking about how to fill electrons in subshells. We haven't discussed orbitals first. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. But that's just rote learning it. That's literally rote learning it. The idea is that you fill out the lowest principal quantum numbers first, and you fill out the s before the d, the s before the d, because 4s is at a lower energy level than the 3d. That's the idea behind it. And I may also have certain pictures to show you. That's how you fill it out. See, that's what teachers show you. This is what teachers teach you. So 1s, then fill out the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then 3d, 4p, 5s, 4d, 5p, 4f, 5d. But this is not in your course. You'll just be asked till 4p, not more than 4p or 5s. You won't go to the 4d stuff. So that's all there is in your course. This beauty right here. Probably till here. This is also very extensive, but yeah, you won't go to the 4f. 4f is not in your course. Yeah, pretty easy, huh? But because I am me, I will teach you some really missed classes with you. Haram, I've missed you guys too. Now, because I'm me, I will also teach you a new way. A way that most teachers themselves don't know, but I am going to teach it to you because I am me. What is that way called? That way is called the periodic table approach. Have you guys heard about this before? Have you guys heard about the periodic table approach? Periodic table approach. And now I won't have to do literally anything. Everything is already done in the periodic table for me. Loving your classes so far, sir. Hasib, love you too. I missed you guys. Yeah. Now, if I look at the periodic table, let me show you the periodic table. Oh yes, that's the A-level periodic table. So, if I look at the periodic table, it looks like a very handy dandy periodic table with you. That's our A-level periodic table because, it has these beautiful decimal points. In O-levels, they just round it off for you. In A-levels, they give you in terms of decimal points, the reality, 1 dp, 1 dp, whatever. Doesn't really matter. But the periodic table, everybody, is basically divided into the idea of blocks. The periodic table is divided into the idea of blocks. Now, how are these blocks decided? Well, these blocks are decided based on the number of outermost electrons. Based on the number of outermost electrons, these blocks are going to be decided. Now, what do I mean by this? Well, what I mean by this is that if the outermost electron is in the s orbital, it's gonna go in the s block of the periodic table. If the outermost electron or the valence electron is in the p orbital, it's gonna go in the p block of the periodic table. If the outermost electron is in the d orbital, and now you're going to get the hang of it. If it's in the d orbital, it's going to go into the d block of the periodic table. If it's in the f orbital, the outermost electron, if that's in the f orbital, is going to go in the f block of the periodic table. Now the question is, where is the f block, where is the s block, where is the p block, where is the d block in the periodic table? This block right here, this block, where you have group 1 and group 2, this block right here, that's the S block. That's the S block. And hydrogen, hydrogen and helium, hydrogen really doesn't have a group, but hydrogen is clubbed here in the S block right here. It's not shown in your periodic table, but it's clubbed right here. Because if you look at hydrogen, how many electrons does hydrogen have? It only has 1 electron. So if I write the electronic configuration for it, it's 1s1. So the outermost electron for hydrogen is in the s orbital. That's why we club it right here in the s block. Helium is an exception. Helium's outermost electron, helium has how many electrons? Helium has 2 electrons, right? In total, that's the outermost as well. So helium, if I want to write the electronic configuration of helium, it's 1s2, the subshell electronic configuration. So the outermost electron of helium is in the s orbital, but that's an exception, although we should have clubbed it here because I'm calling these two blocks the s block, but this is also gonna come under the umbrella of s. Although it's not here, although helium and hydrogen are not here, they are both clubbed under the S block. Because helium also has noble gas properties and whatnot, that's why it's clubbed here. But helium and hydrogen also are, they are an exception, so you can imagine them to be here. They're not, but you can imagine them to be here, right? Now, that's the S block. Where is the D block, everybody? This beauty right here. This beauty right here is the D block of the periodic table. Now, why are elements in the D block? Because they have the outermost electron is in the d orbital. They have the electron, the valence electron of all of these elements is going to be in the d orbital. Next question. This, my dear fellas, this right here, this green stuff, all of this green stuff. This stuff right here is the P block. Why am I calling this the P block? Because all the electrons that these elements have, all the outermost electrons of these elements are going to be in the P block. Yes? So, in the P orbital. So because all of these elements have their outermost electrons in the P orbital, that's why this block is called the P block. And these two are not our concern, but these two are the F blocks. Why? Because the outermost electrons of all of these elements right here, they are going to be in the F orbital. So that's the P. One is the S block right here. That's the S block. That's the D block. That's the P block. Hydrogen and helium are exception. They're not, but you can imagine them to be clubbed in the S block. So helium is not in the, it's not here, but it still corroborates with the S block. Hydrogen is not here, but it still corroborates with the S block. You can imagine these two to be here. Okay. Now, and this is my F block, that's the D block, that's the S block, and that's the P block. Now, why in the hell do we need to know about these blocks? Why in the hell do we need to know about these blocks? Why? I'll tell you why. Because I'm going to teach you the electronic configuration through it. You need to know about these blocks because these blocks actually tell you the electronic configuration. Wait, let me figure out a better picture for you. Is this better? No, I don't like this. I want to go with, there was a picture that I saw. Okay, we don't have that one, so I'll just take this one. The reason why you need to know about these blocks is that the blocks actually tells you the electronic configuration. How beautiful is that? How beautiful is that? Sir, what do you mean by this? How does it tell us the electronic configuration? How in the world? Well, you'll realize that if I'm saying that this is the S block, this is 1S1, that's 1S2 right here. These two are exceptions, right? And after this, this is the second shell, right? This is the second, because you know the lower you go in the periodic table, this was the first row. So first row means first period. First period means principal quantum number one shell. Second row means second period. Second period means two shells. Two shell means principal quantum number 2. So that's 2. And so this would be 2s1. This would be 2s2. And then you move on to boron right here. That's P1, P2, P3, P4, P5. And the last but not least, that's P6. This is D1, D2, D3, D4, D5, D6. And trust me, this is the best way to write the electronic configuration. D7, D8, D9, and D10 right here. And obviously this is F1, F2, and that's not in our code, so I'm not going to go into F, right? But it's going to go till 14. And this is S1 right here, and that's S2. Now what you need to do is, if I say tell me the electronic configuration of boron, so how do you do it? Well, you say it's 1s1, 1s2, so it's 1s2 right here. Then you come on to the second block, 2s1, 2s2, so 2s is also filled, 2s2, and then you move on here. This is 2 because it's the second period, so it's the 2 and P1, so it's 2P1. That's how you do it, by just looking at the periodic table. And you need just a little practice with this. Again, if I were to say, tell me the electronic configuration of nitrogen, you could literally do it by looking at the periodic table. It's 1s1, 1s2, so 1s2, 2s2, 2p3, 1, 2, 3. So 1s2, 2s2, 2p3. Easy. I don't even have to think. I literally don't have to think. What if I ask you, tell me the electronic configuration of chlorine? Can I do it? Absolutely. This is 1s2, these two combined, 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5, 3p5. So it's 1s2, 2s2, 2p6, 3s2, and this is 3p1, 2, 3, 4, 5, 3p5. I bet most of you didn't know this. And this is shown right here. See? This is the second period. So 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2. If an element is present here, let's suppose an element is present here. Not here, sorry. If an element is present, let's suppose here. Can you guys tell me the electronic configuration for it? If an element is present here, by just looking at the periodic table, can you guys tell me the electronic configuration? Absolutely I can. So 1s2, this would give me what? 2s2, 1s2, and that's 2s2, 2p6, 3s2, 3p6, and see, it's even filling the 4s for you. This is so beautiful that the periodic table approach can also, mitigate an error. It will fill the 4s2 first for you, and then you move on to 3d10, and then it's 4p1, 2, 3. So how do you write my electronic configuration? It's like 1s2, 2s2, 2p6, 3s2, 3p6. See, even here, it's even, mitigating the risk of getting this wrong. Because if you use the periodic table approach, after you fill out the 3p, it will automatically first tell you to fill out the 4s, But you write it here. So 4s2 is filled first, and then 3d10 is filled, and then 4p1, 2, 3. So 3d10 and 4p3. How easy, guys. Again, I want you guys to tell me the electronic configuration of this beauty right here, this element. Tell me the electronic configuration of rubidium right here. Can anybody tell me the electronic configuration of rubidium? See, I've segregated the entire periodic table into blocks. So you first go like this. You say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. You know, because that's 3d10, 4p, because it's the fourth stuff you're talking about, right? This is 1, 2, that's 3, that's 4, that's 5, that's 6, right? So how do you fill it? Well, 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s2, 3d10, 4p what? 4p6, 5s2, right here. So it's 5s1, not 2, because 2 would be strontium. So rubidium is 5s1. So you could use the periodic table approach even, and this is what I always used because it's the easiest approach to use, but it's up to you. If you want to, say, oh, rubidium has 37 electrons, and then you write 1s, 2s, 2p, 3s, 3p, 3d, 4s, all, first of all, you make this for yourself, this pathetic trick for yourself that this is 4p, 4d, 4f, and then you start filling it. Okay, 2 goes here, okay, 2 minus, then 2 goes here, then 6 goes here, then 2 goes here, so in total 8 goes here, then 6 plus 2 goes here, and then 10 goes here, and then 6 go here. This takes a lot of time. So what do? We literally use the periodic table approach. We say, hey, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because d starts from 3. Principal quantum number 3 actually has the d orbitals. So that's how easy it is. Can anybody tell me the electronic configuration of phosphorus from the periodic table approach? Phosphorus. Can somebody tell me the periodic table? Can somebody tell me the electronic configuration of phosphorus using the periodic table approach? You always start here. Okay, P is here, so I'll have to start from the first element and start filling the electrons until I reach P. So 1s1, 1s2, so that's 1s2, 2s2, 2p6, 3s2, 3p3. Boom. That's it. That's the electronic configuration for it. No, it's not 2p3. Why is it 2p3? It's 3p3. This is 1, this is 2, this is 3. Right here, this is 3. That's the third row. Right here. D, why am I calling this 3D, not 4D? Because D orbital starts with 3. So this is 3, 4, 5. That's the D orbitals. The D orbital starts with 3. Principal quantum number 3. Right? Can somebody tell me the electronic configuration of fluorine using the periodic table approach? Fluorine. It's what? 1s1, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 2p5. Somebody tell me the electronic configuration of neon. 1s2, 2s2, 2p6. Somebody tell me the electronic configuration of magnesium. 1s2, 2s2, 2p6, 3s2. Somebody tell me the electronic configuration of potassium. Right here, potassium. How do you tell me the electronic configuration of potassium, everybody? Well, 1s1, 1s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The SC, remember? 4s is filled before the 3d. 4s, and the periodic table will always make sure that you fill the 4s before the 3d. That's why I love this approach. Because you don't even have to think. You literally don't have to think. How easy is it? Can somebody tell me the electronic configuration of calcium? Now, one way to do it is start filling out all the 20 electrons, write it like this, and then 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. One way is this. And the other way, pretty easy. What way? Well, what way, guys? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Boom shakalaka, boom shakalaka. Remember, this is not 4D. This starts 3D. D orbital starts with the number 3, not with the number 4. Yeah? Makes sense? Kitna aasan tha? How many of you guys knew this approach before this? And see, before the 6S, the periodic table approach is whenever you start to fill out the 5D, before the 5D, you need to fill out the 4F right here. But nobody cares, because F would never be there. So this is the reality, This is how you can actually use it, but we'll just be asked to use it till this point right here, not more than this point. So above all of this, this is our job. Below this, not our job. Did you guys know this before? I have a question. Did you guys actually know this before or no? I love this approach. Noor Usman, thank you, thank you. You guys didn't know this? Well, now you guys can teach your friends. Nope, nope, nope. Oh my god, what are the teachers doing in school? I did, but not in detail. Well, now you do. This approach is so Gucci. Can somebody tell me the electronic configuration of germanium by using the periodic table approach? Of germanium, everybody. Now, instead of this has become very disgusting, so I'll add the periodic table again. That's why periodic table should be your best friend in O levels. In A levels. So, I want germanium, please. Yes. So, what do I say? I say, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then, what is this? See, this was 2, this was 2p, 3p, 4p. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2. Why am I calling this 4? See, because p starts with 2. Or if you want me to, label it for you, this is the s. In the pink, I'm writing the s starting points. In the pink, that's the s. In the blue, that's the d, 3, 4, 5, 6, whatever. And in the green, that's the p. So you start with the p orbital from principal quantum number 2. You don't have, you can't call this 1. You can't call this 1 because the p orbital starts with principal quantum number 2. In principal quantum number 1, you only have the s orbital. So that's 2, 3, 4, 5, 6. You can also, take a screenshot of this to remember it forever. So if I want germanium, what is this? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p2. Easy peasy lemon squeezy. Now, the reason why I wanted you guys to know this approach is I wouldn't have taught you guys this approach if I did not find it useful to teach it. And the reason why I've taught it to you guys because it's very useful in writing shorthand electronic configuration, which the examiner now has started to test. I was reading the syllabus in our time, this was never tested. Not much. Shorthand electronic configuration. In our time, this was not taught. And this was not even tested. But now I'm glad that they have started testing shorthand electronic configuration. Remember, by electronic configuration in A levels, I mean subshell electronic configuration. We haven't studied orbital electronic configuration. We'll do that tomorrow. But subshell, I want to, solidify subshell electronic configuration for you. Now, if I want you guys to write down the electronic configuration of potassium, can you guys tell it to me? The electronic configuration, tell me through two ways. First, tell me through the normal way, which is 1s2, then 2s2, 2p6, 3s2, 3p6, and then instead of filling the D, I know that S comes before the D because 4s is at a lower energy level. So it's 4s1. True? And now I can use the periodic table approach. What's the periodic table approach? Potassium is right here. So that's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Easy. Isn't it? Isn't it easy? I don't even have to think. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. हर चीज सिखाऊंगा. I will teach you to think through so many ways that you'll never gonna get confused. You'll never be confused. Never, ever, ever. Inshallah. Now, what is shorthand electronic configuration? Well, shorthand electronic configuration helps you focus on the outermost electrons. Helps you mainly focus on the outermost electrons. And you know that the outermost electrons are present in the highest principal quantum number. So if this is principal quantum number 1, that's 2, that's 3, that's 4. So in the highest principal quantum number, you have the outermost electrons, and in this case, it's in the 4s. So the s subshell has 1 electron. So the outermost electron for potassium is 1 because the outermost electron, the outermost subshell that you have is the 4s subshell, and it only has 1 electron, right? Now, shorthand electronic configuration firstly helps you focus on the outermost electrons, and number 1, you focus on the outermost electrons, and number 2, it also helps you, it's easier to write long electronic configuration. You shorten it up, so easier to, write long electronic configuration. Instead of writing long electronic configuration, you use the shorthand electronic configuration. Now, what in the hell is shorthand electronic? I literally love this word. What in the hell is shorthand electronic configuration? Well, shorthand electronic configuration, what you do is you write the noble gas before it in brackets. So instead of writing all of this, what you do is you write the noble gas, the symbol of the noble gas in brackets before it. What do I mean by this? Well, what I mean by this is, if I talk about potassium, what is the noble gas that came before it? What is the noble gas that came before potassium? That's argon right here. That's noble gas, right? So what I do is, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, I call all of this combined argon. So I'm going to say, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, I call this argon. I call this argon, Ar. And I put two brackets right here. What this means is that this particular element has all of this inside it. All of this. 1s2, 2s2, 2p6, 3s2, 3p6, all of this is present inside, argon's electronic configuration. This is what argon's electronic configuration is like. So what you do is, you look at the element, and then you look at the noble gas that comes before it. So that's argon. It has 18 electrons. So what you do is, you take all of these 18 electrons and just call it argon. And then what is left behind? 4s1 is left behind. So if I were to write the shorthand electronic configuration for potassium, I'd just write argon 4s1. That's it. Argon 4s1. What if I want you guys to write the shorthand electronic configuration of calcium? Do it on your own now. Well, you go to calcium and you see which noble gas comes before calcium. Well, it's argon. So 18 electrons are already inbuilt when I write argon. What about these two? Then it's 4s1, 4s2. So argon, 4s2 is calcium. See? And it's helping me focus on the outermost electrons. How many outermost electrons does calcium have? 2. How many outermost? That's why it's in group 2. How many outermost electrons does potassium have? 1. That's why it's in group 1. So we shorten it. Yes, Aisha. And this is what the examiner has started to ask in your level now. For your level, the examiner has started. Don't write the other brackets. Sir, ye to absolute cinema hai. Thank you. Welcome. Sir, never heard of this, but this is fun. Well, you should have heard of this. No, Abdurrahman, it's not P and D before the S. No, nothing like that. Just remember, it's always S before the D. But D or S में ये कहानी चल रही होती है. What if I want you guys to write the shorthand electronic configuration of maybe like boron? Well, normally you don't need to write shorthand electronic configuration for boron, but let's suppose I wanted you to write it. So well, what I do is I look at the noble gas that came before it, which is helium, and I put two brackets. Don't put curly brackets or parentheses. Put square brackets. So helium, so 2 electrons are here, and then it's 2s2, 2p1. So helium, 2s2, 2p1. That's it. How easy, guys. Literally. A-level, sir, the most questions I ever used to get when I stopped teaching A-level, sir, how do we do electronic configuration? We don't understand it in A-levels. What in the hell is this? Well, now you do. Okay, can you guys tell me for chlorine, shorthand electronic configuration? See, now if you're good with the periodic table approach, what you will do is, instead of writing, first writing it down and then corroborating it with noble gas and blah, 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 you can just literally look at this periodic table and say, hey, I need the shorthand electronic configuration of chlorine. Well, that's neon, 3s2, 3p5. Neon, 3s2, 3p5. Done. That's it. And you guys would be the quickest out of all your friends. 3s2, 3p5. Remember, this is not 1 and this is not 2. 1p does not exist. P starts from 2. D starts from 3. And obviously the S starts from 1. So 1, 2, 3, 4, 5, 6. And D starts from 3. Principal quantum number 3. And P starts from principal quantum number 2. कितना आसान है, मजा आ रहा है? अच्छा, can somebody tell me for the shorthand electronic configuration for bromine? Yes. तेरे नैना रे. Can somebody tell me the shorthand electronic configuration? And also tell me the proper electronic configuration for bromine. Yes, maja. What about Ni? Well, okay. After bromine, do Ni, do nickel. After bromine, somebody do nickel. So how do you do it for a bromine? Well, so before this, it's argon, and then it's 4s2, 3d10, and 4p, 1, 2, 3, 4, 5, 4p5. That's it. So I'm going to write it for you. For bromine, it's going to be what? It is argon. Argon is the noble gas that is immediately before it, and it's 4s2, 3d10, 4p5. So 4s2, 3d10, 4s2, and 4p5. See, I filled out the 4s before the 3d, but I wrote the 3d before the 4s, right? Because Cambridge clubs, principal quantum numbers together. So it says instead of writing 4s2, 3d10, 4p5, write it 3d10, 4s2, 4p5. But either or is correct, but Cambridge clubs 4 and 4 together, 3 and 3s together, 2s and 2s together, right? But remember, you always fill out what? 4s before the 3d. See, I filled this out first, 4s2, but I wrote 3d first. Wrote it first, but filled 4s first. So why? Why do you fill out 4s before the 3d? Why? Because it is at a lower energy level. Somebody do for nickel, because somebody asked, can somebody write the shorthand electronic configuration for nickel? Well, it's argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 3d8. Easy peasy lemon squeezy. We're not done yet. There's a problem. There is a slight problem, but that problem I think we will discuss tomorrow. You're not completely done. You're not completely done. There's one slight catch, and that's called the periodic table error. I call it. So periodic table is Gucci on and all, but there's one error it's gonna give you. Only one error. Only one error. And that is when you start talking about, when you start talking about chromium, and when you start talking about one other element, which is copper. So when you start talking about chromium and copper, it's going to give you an error. And this error, these two errors, we'll discuss tomorrow, and you'll be done with electronic configuration for subshells. I have not discussed electronic configuration of orbitals. I have only discussed electronic configuration, writing electronic configuration through subshells. Orbitals, I just give you a glimpse when I was teaching sodium. When I was teaching sodium to you guys, I said, hey, if I want to write the electronic configuration in terms of principal quantum number, that's 281. If I want to write it in terms of subshells, so it's 1s2, 2s2, and 2p6, and 3s1, right? That's what? 11 electrons. 4 plus 6, that's 10, and then it's 11. And if I want to write it in orbitals, so now I'm going to say, hey, 1s2 orbital, 2s2 orbital, and 2p2 orbital, 2px, 2py, 2pz. And that's 2, 2, and then 3s orbital has only one electron. So this is in terms of orbital, and we'll discuss more of this on Saturday. Tomorrow I want to finish this off for you guys. Do you want me to finish it off today or tomorrow? और आज के लिए इतना दिमाग फ्राई हो गया है. Because there's one problem in this approach. Only one. The other approaches have their own problems. Periodic table will only give you a problem here. That's what I call the periodic table error with copper and chromium. And you learn that. That's an exception. That's the last exception in your course. And you'll be done. You'll be done with electronic configuration. No person in the history would ever get you guys wrong with it. Today, Mohib is saying do it today. Today, everybody's saying today. Okay, you guys are probably enjoying it. But it's a little technical concept. I don't want you guys to, just go, sir, is this the first non-demo class after lesson 3? Yes. You guys can make me more and more famous. Oh yeah, I'll talk about general things. Instead of teaching you guys the concept between copper and chromium, I'll just teach you guys general stuff. And that general stuff is, you may be tested on this. It's pretty logical. So I'll teach you that general stuff. Like, for example, I show you this. What if the examiner asks you, what's the difference between the 1s orbital and the 2s orbital? Because now I'm not talking about subshells anymore. We're done with subshells. Just one exception, we'll do that tomorrow. I'm just talking about orbitals. We studied orbitals in the last class. What are orbitals? Orbitals are regions of space where there's regions in space where there's a 95% chance or probability of finding an electron, and it can hold a maximum of only 2 electrons, right? What's the difference between the 1s orbital and the 2s orbital? There are two differences between them. What are the two differences between the 1s and the 2s? Two differences. Yes, Rayan, this is AS level. We're doing AS level class. It's not O level class. Yes, thank you. बहुत शुक्रिया. ये O level वाले बच्चे मेरे बगैर रो रहे होते हैं सारा दिन, इसलिए आके AS में भी बैठ जाते हैं. What's the difference between 1s? There are two essential differences between 1s and 2s. Number one is the difference in their size. You could literally even see the difference. One is the difference between size. What is the difference? Well, the 2s is greater in size compared to 1s. Ain't that true? It's larger. 2s is larger than 1s. If the examiner were to ever ask you, and no teacher is going to tell you this because it's pretty logical. And the other one is in energy. The 2s is at a higher energy level than 1s. You know, you first fill out 1s, then you come to 2s. So 1s as it is at a lower energy level, which means it is closer to the nucleus. 2s is farther away from the nucleus. And the more distance you are from the nucleus, the more energy you have. Because realize, if I start to pull you guys towards me, come to the chemistry class, will a person, you know, let's suppose this is Mohib. Let's suppose this is Mohib, you know. And if I pull Mohib towards myself, he's right here. Mohib like, sir, I don't have enough energy. You can pull me closer towards yourself. But then there is Ali, and Ali is right here. I'm trying to pull Ali, but Ali is far away from me, which means Ali has more energy. Ali is further away from me. I am a positive charge. I'm the nucleus. So realize that the 2s has more energy than the 1s. Is at a higher energy level than the 1s because it's further away from the nucleus. That's how scientists do. So that's the difference between the 1s and the 2s. And similarly, if I were to make 3s would even be larger in size. So the higher principal quantum number you have, the larger the size gets, right? And also realize one more thing. The 2s, this is just fun facts for you guys because I don't want to go into that detail for now. The 2s is more diffused. What does that mean? What does this stuff mean? The 2s is more diffused. याद रखें, I'm teaching a model batch. The reason why I'm calling this model batch, I will give you all the knowledge in the world along with very, very, very high level of precision and practice. And the reason for that is that I may not be able to teach AS level ever again. So you guys are lucky, and I'm going to teach everything to you guys which makes sense in your course to be taught to you. You know, conceptually, I want to make you guys so sound that later on these recordings would be watched by students. So you guys are the only ones who are taking the live classes. Now, what does this mean? 2s is more diffused than 1s. I can also call this as, I can also rephrase it by saying 2s has a lower charge density. What does this mean? What in the hell does this mean? Sir, what in the hell are you writing? Has a lower charge density, is more diffused. Well, this means, you know, if I say that the orbitals have a maximum of 2 electrons, right? Maximum of 2 electrons, right? Orbitals have maximum of 2 electrons. Can you guys tell me which one has a higher volume? What is density, guys? What is density? Density is mass over volume, right? And in this case, I'm looking at the charge. So I'm talking about charge density. How much charge is there in a particular volume, right? So if I look at the charge density, can you guys tell me something? Which one would have a higher charge density and which one would have a lower charge density? Obviously, the 2s has a lower charge density. It's more diffused. What this means is it has a higher volume. It has a larger volume, not higher. It has a larger volume compared to 1s for the same amount of charge. So the charge is more diffused in the 2s compared to the 1s. It's more concentrated in the 1s because it's smaller in size. You know, so that's also a difference. So these are, you know, three differences that you could know: size, energy, and then charge. So 2s has a lower charge density because it has a larger volume, so the charge is more spread. 1s has a higher charge density than the 2s because the charge is more concentrated since it has a smaller volume. Yeah, make sense? Yeah. चलो एक और बात भी बता देता हूँ. नहीं, एक और बात भी सुन लो. One more thing, you know, if I talk about p orbitals, if I make the px, the py, and the pz together, it looks like this, a flower. You know, I can also show you the picture for it. It looks like a flower, like this. This is how it looks. And the beauty about these p orbitals is, can you guys tell me, if I draw x-axis, y-axis, and z-axis for you guys, what are the angles between x-axis, y-axis, and z-axis? What are the angles between x, y, and z? What are the axes? It's 90, you know? They're all 90, 90, 90, 90. If you know your math, you know that all these axes are at 90 degrees to each other. So can you guys tell me, the px and the py and the pz, are they going to be at 90 degrees to each other, or 195, 4, 3, 2, 1? What is going to be the angle between the px, the py, and the pz? That's obviously also going to be 90 degrees, not Celsius, just 90. You know, because the axes are at 90 degree to each other, that's why the px, the py, the pz are also at 90 degree to each other. And what if I say you have 3p6, right? And you have 2p6. I'm just comparing the p orbitals. Now, obviously, the 3p6 is at a higher energy level. Obviously, it's larger than in size, and it's more diffused. Larger in size and more diffused. It has a lower charge density. You know, it is more diffused, or you could say has a lower charge density. Denser. You know, you could say that. But one more thing. What if I talk about the p orbitals in 3p6? You know, if I talk about the p orbitals in the p subshell, in the 3p subshell. This is orbital number 1, let's suppose. That's orbital number 2, and that's orbital number 3. Sorry for my pathetic drawing, but yeah, that's 3px, 3py, 3pz. My question to you guys is that obviously, the 3p, the 3p subshell, or the 3p orbital, if I talk about it, it's at a higher energy level than 2p, it's larger in size than the 2p, it's more diffused than the 2p. But what about the same subshell and the same orbitals, 3px, 3py, 3pz? Can you guys tell me which of these would have a higher energy, 3px, 3py, or 3pz? Zoha, axis determine the perspective. Whether you're looking at it from the top, the bottom, the side, the left, the right, it's just a three-dimensional space. My question to you guys is, are electrons in the 3p subshell, will electrons in the 3p subshell all be at the same energy level or different energy levels? In the 3p, I'm not comparing 3p to 2p. I'm just saying in the same subshell, are they going to be in the same energy level, these electrons, or are they going to be in different energy levels? Obviously, they're going to have the same energy levels because the subshell is the same. So energy levels are determined by subshells. That's why they're also called sublevels. Remember when Erwin Schrödinger started to knock off electrons, 6 electrons had same energy, and then 2 electrons did not have the same energy in principal quantum number 2. Although these 6 electrons, let's suppose it is 2px, 2py, or 2pz, or 3px, 3py, 3pz, doesn't really matter, but they all will have the same energy. So remember, p orbitals within the same subshell are going to have the same energy level. Or you could say orbitals, not just p, it applies to all orbitals. Orbitals within a subshell, orbitals within a subshell are at the same energy level. These are things which are tested in MCQs. I'm not even joking. And that's why teachers say MCQs are the most difficult. But I say that MCQs are the easiest. Because if I make sure that your concepts are strong, your theory is strong, your MCQs will always be strong. Aisha says, I feel so motivated after your classes. I'm glad, Aisha. Love it. Abdul Rahim, no, not at different energy level, huh? At the same energy level. Because see, what is a subshell? Abdul Rahim, go back to the basics. What is a subshell? It's an orbital or a combination of orbitals, you know. So if it's the p subshell, it's the combination of px, py, pz. If it's the d subshell, it's a combination of all the 5d orbitals, which will all be at the same energy level. Only the s, p, d, f would be at different energy. Different subshells are at different energy levels, but orbitals in the same subshell are all going to be at the same energy level. This much clarity I don't think you're going to get anywhere else but here. Acha, one more question. A student is asking, sir, why does the orbital have a maximum of 2 electrons? Why not more than 2? That's a very good question, and you learn more mathematics behind it if you pursue chemistry in university level. You'll learn M sub L and all the principal quantum numbers. But for now, it's not in your course. But I'll tell you why an orbital can only hold a maximum of 2 electrons. Because there are only 2 spins available. A maximum. Examiner can never ask you this, but if he ever asks you, you can say there are only 2 spins available. What does that mean? Well, if one electron is spinning clockwise, the other electron would spin anti-clockwise. These are the only 2 spins available for you. I can even show you the picture for this. I can even show you the picture. This picture. I'll show you all of this later on as well. But I'll show you the picture. Look at this. If one is going clockwise, one electron, this arrow is representing an electron. So if one electron is going clockwise, the other goes anti-clockwise. And these are the only 2 unique spins available. There can only be 2 unique spins. And Schrodinger proved that through complex mathematical equations which are not in your course. So yes, there are only 2 unique spins. That's why an orbital, 2 unique spins only. That's why an orbital only has a maximum of 2 electrons. Not more than 2, because you only have 2 unique spins. Hi, sir, I've already made you famous in my class. I'm glad, Bilal. Thank you. Any questions, guys? Asanta. Can somebody tell me using the periodic table last? Can somebody tell me the electronic configuration, the shorthand electronic configuration and the proper electronic configuration of sulfur? Shorthand and proper. Now you guys can do it very quickly. And then also tell me for selenium, sulfur and selenium, shorthand and the complete one. Now I've taught you all the ways, and it's your choice whichever way you want to stick with. Want to stick with the logic, want to stick with this way, or want to stick with the periodic table method. That's all up to you guys. So Aisha is saying it's neon. Yes, so Bilal, you don't have to write the word neon, just write the symbol. So Ne, neon, and that's the shorthand, right? So neon 3s2 3p4, neon 3s2 3p4. That's it. Yes, everybody's right. 3s2 3p4. Awesome. Yeah, but what about selenium? What about this? So it's argon 4s2 3d10 and 4p4, because this is 2 3 4. So 4p4 3d10. But remember, I will always fill it like this, that this is 4s2 3d10 and 4p4. But Cambridge says always write the principal quantum number, club them together. So you're going to write argon 3d10 4s2 4p4. Although saying argon 4s2 3d10 4p4, that's also correct. But Cambridge just clubs the principal quantum numbers together. Yes, thank you, Aisha. Awesome. Aisha is saying the proper electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Awesome. मजा आ रहा है वैसे. Would they deduct marks if we don't club them together? Abdurrahman, probably not, but this is what they've said in the syllabus, and I'm teaching this syllabus. So it's up to you. In other boards, probably it doesn't matter, but yeah. Sir, it's fun, to be honest. It is fun, Noor. Thank you. Mohib, yes, awesome. It's time we get 1 billion students after this crazy stuff. Guys, I have a question. So I've said that the syllabus will be over in 6 to 7 months, right? And obviously, inshallah, in 7 months, to khatam ho jayega. But what if it goes to 8 months? Would it be fine with you guys or no? Would you guys want me to finish it off in 7 months? Is it going to be fine if it goes till 8 months? Because I want to do all the practice as well. I don't want to leave you guys with just concepts. Hasib is saying no more than 7 months, sir. No more than 7. I want you guys to be so ready, because, I'll tell you something, guys. I'll stop the recording and I'll tell you something. वैसे तो 7 months ही होगा, inshallah. Don't worry. 7 months ही होगा, inshallah. But I'm saying, would that be a problem if it goes to maybe 7.5, maybe? Because the thing is, I want to do all the questions in the class. You guys are my model batch. You guys are my model batch.